All right, back to this problem where we've got a beam pivoted at a wall. So this is, look, this is upward in the problem from the earth. It's pivoted here. It would fall down and slap the wall if it weren't for the tension in this light cable that's pulling at an angle of 25 degrees to the horizontal. We've got a heavy lantern here. We know its mass, and we know the mass of that beam. The beam has a uniform density all the way across it. So its center of mass is going to be right in the middle. All right, so let's put some unknowns into there. Here's my picture. I'm going to take counterclockwise to be the positive rotation direction. In this case, there's a pretty obvious rotation axis, and it's a good choice by what I told you in the last problem anyways, because look, Fx and Fy, those force components, are both acting at this pivot point. So they're not going to appear in the torque equations if I sum torques about this pivot point. I could sum torques about maybe the center of mass, but then all three of these variables would come into the torque equation. So we're choosing judiciously here to sum torques about there. So I'm going to take upward to be plus y and to the right to be x. I've put some forces on here, the weight force of the beam, the weight force of the lantern that's on the end, and an unknown T for the tension in the cable. And let's just start digging into it. Sum of the forces equals 0 along the x direction. So notice that 3 of the forces have only non-zero y components, so they don't come into the x equation. The only forces that have non-zero x components are my unknown Fx and the x component of T. Fx is going to come in with a plus sign, and the horizontal component of this is T times the cosine of 25, and that comes in with a negative sign because it's pulling more or less in the negative x direction. Those add to 0. I've got two unknowns in there, so I'm just going to hold on to that equation. Let's sum forces components along the y direction and set those equal to 0. Here I've got 4 different components, right? I've got my unknown Fy here. I've got this weight force, I've got this weight force, and the vertical component of T. So Fy and the T things coming with plus signs, and the 2 weight forces coming with minus signs, and they have to add to 0. Again, 2 unknowns. They're different unknowns because here I got an Fy down here instead of Fx, so I'm just going to hold on to that equation and work with it later. Now the sum of the torques, and this is the one that's really nice because we've chosen to sum torques about this pivot point. Fx and Fy don't come into it. My only other variable that's in there is T, so I'm going to be able to solve for T using this. I'm going to use the form of the torque where we take that distance r from the axis of rotation to the point at which the force is being applied, and then we multiply by the perpendicular component of the force. To get the perpendicular component to r of t, what we have to do is multiply by the sine of 25 to give us this vertical component of that force. So I get t times the sine of 25 multiplied by r, which is 2 meters. That comes in with a plus sign because that t is trying to rotate it in the positive direction. And then I have 2 other forces that are exerting negative torques. Both of these weight forces are trying to make it rotate in the negative direction. So both come in with minus signs. 300 times 9.8, the weight of the beam, has a moment arm, which is half, it's as if it's being applied at the center of mass, so its moment arm is 1 meter. And the 100 times 9.8 has a moment arm of 2 meters. Both those come in with minus signs. That is a nice equation because it allows us to solve directly for T. So T is 5,800 newtons. Now I can go plug that T into both the first and the second equation. Plugging into the first gives us Fx is 5,250 newtons, and into the second equation gives us Fy is 1,470 newtons. So that, engineers like to do this kind of stuff because they say, oh, how big and beefy of a pivot do we need here? How strong of a cable can we use here? Clearly we don't want to use weak fishing line or something like that. It might have to be a pretty hefty cable. It's got to stand 5,800 newtons of tension, so that tells the engineers how big they have to, how bulky these items have to be to support the weights that are needed. Okay, next problem in our long worksheet, it involves your arm. So here we've got a very crude model of how your arm works. We've got the elbow joint here. We're imagining we've got our upper arm here vertical and then our forearm horizontal, and we're extending it and holding a ball in our hand. It's 5 kilogram ball held in our hand. And we're told that relative to the elbow joint, the ball's center is 35 centimeters from the elbow joint. And if that were the only thing happening, of course, the whole forearm would go down. Why doesn't the whole forearm just give way under its own weight or the weight of the ball and just flop downward? It's because the biceps muscle. The biceps muscle, the key thing is that it's not attached at the elbow joint, but it's actually attached a little bit out from the elbow joint, a distance of 5 centimeters out from the elbow joint, and it pulls upward. So it's trying to rotate the forearm in this direction, whereas the weight of the ball is trying to rotate it in the opposite direction, and the weight of the forearm itself, we're told something about that. The center of mass of the forearm is 15 centimeters from the elbow joint, and we're told the weight of the mass of the forearm itself is 2 kilograms. So that's also trying to rotate it in the clockwise direction. So we have all the information we need. If the biceps muscle pulls just the right amount, everything will be in equilibrium. So let's find the force the biceps muscle has to exert on the arm to hold it steady. And then also, there's a force that I haven't mentioned yet, which is the downward force of the upper arm on the elbow joint, or on the forearm through the elbow joint, which has to be pushing down. In other words, if the elbow joint weren't pushing downward on the forearm at this location, then by virtue of the biceps muscle pulling up and these two going down, the whole arm would start to rotate in this direction and not be in equilibrium. So the upper arm has to be pushing downward on the forearm at the elbow joint. And the question is, how big of a force does it have to exert there? Okay, let's start digging into it. The first thing we're going to do is give some sign conventions. Plus y will be up. Nothing interesting is happening in the x direction, so we don't have to worry about that. I'm going to take the usual, or at least more common one, counterclockwise to be the positive rotation direction. And because there is a joint there, the elbow joint, I'm just going to take that to be the point I sum torques about. Okay? Let's first do f net y equals 0. There are lots of, it looks like 4 different forces that have non-zero y components. F1, I guess I'm calling it F1. I guess I misread it here. It looks like it's actually an FJ for joint or whatever, but I called it F1 here. F1 is going downward, right? It has to push downward. So it's negative. F of the forearm weight itself is downward, so it comes in with a minus sign. The ball is also downward, so 3 of them are going to come in with minus signs. The only one that's positive is Fm for the muscle, the biceps muscle. That comes in with a plus sign. So if we add all those up, we still have 2 unknowns in here, so I can't solve for either F1 or Fm right away. But undaunted, let's set the sum of the torques equal to 0 about the about the elbow joint. Let's see. The biceps muscle is pulling upward. That's trying to rotate it in the positive direction, and it has a moment arm of 5 centimeters, or 0.05 meters. So that one comes in with a plus sign, force times moment arm, and the other two coming with minus signs because they're trying to both these weights are trying to rotate it in the negative direction. So they have minus signs, and the moment arms are 15 centimeters and 35 centimeters. That's why I get a 0.15 and a 0.35 there. Set those torques all to add to 0, and that allows me to solve for what Fm is, 401 newtons upward. And then once I've got Fm, that biceps muscle tension, what I can do is plug it into the first equation to get the F1 or the Fj. I think it's actually supposed to be there, and it's 332.4 newtons. So that tells us something about, let's just point out something interesting here. The weight of the ball itself is going to be 5 kilograms times 9.8. So I'm holding an object which is about 50 newtons of force going downward on my hand. Notice that my biceps has to pull up with something that is about almost 10 times as big, right? 10 times as big would be 500 newtons about. This is 400 newtons, so it's getting close to 10 times as big, and that's because the one mass is way out here, whereas the other force is being applied very close into this joint. And so in order to give a counterbalancing force to this weight force, we have to apply a huge force upward here to counteract a smaller force out there. And so you can see the disparity between the weight of the ball you're holding and the muscle force that's required. All right, here's a second variation. The next part, part C asks, suppose you change the orientation of your forearm so it's not being held horizontally anymore, but rather it's 45 degrees below the horizontal. How does the biceps force required change from the 401 newtons that was in the previous problem? And so if we go through the same analysis and do the sum of the forces equal to 0, well, the forces being applied haven't changed anywhere, so we get the first equation exactly the same. It doesn't matter that the arm is rotated, the forces are still all being applied in the vertical direction. They all have the same signs and magnitudes, so the first equation is exactly the same. The second equation isn't the same because notice that the moment arm for example, the forearm weight force has gotten smaller. It used to be being applied out here. It had a bigger moment arm that was 15 centimeters. Now it's going to be 15 centimeters times the sine of 45 degrees, or times the cosine of 45 degrees. I guess there's two ways you can think about it, but in any ways, cosine of 45 and sine of 45 are the same. So you get a factor of sine of 45 multiplying the torque due to the forearm force, also multiplying the torque due to the weight force, and also multiplying the torque due to the biceps muscle force. Same factor of sine of 45 degrees, or you might have written it as cosine of 45 degrees, depending on how you're thinking of calculating the torque. Because the sum of those three has to equal 0, I can just divide both sides of the equation by sine of 45 degrees, and then I find that the second equation reduces to something that's equivalent to what it was in the previous case also. So the two equations are exactly the same as we got before, so same equations, same force for the solutions. So we get the same muscle force and the same elbow force. It's kind of surprising. You might think, oh, it's harder to hold it upwards horizontally, and then maybe it gets easier as you lower your arm down. Now, I will say, in this particular model, that's true. That doesn't matter the angle. A real biceps, we've made sort of an idealized model of it here, and the fact that the biceps muscle is always pulling in the same direction, it doesn't get squashed against the bone and things like that are complications, but at least to a very simple approximation, you don't get to relax any with your biceps muscle as you lower the weight down by 45 degrees from where it was originally. All right, let's finish up this chapter, and mostly this chapter was just to practice doing those problems. So that's the totality of this chapter, is just to work those problems. You get more practice in the homework. Let's finish up with a voting question. A box with its center of mass off-center indicated by the dot. So in all these four cases, the center of mass is located at the dot for the box in question. It's sitting on an inclined plane. In which of the four orientations does the box tip over? A, B, C, and D. The answer is only in case C. And that's because, well, we can think of if it tips over, it's going to start rotating around this lower left point, the point that's touching the plane at the lower edge of it. And in this case, if we pretend, as we always can, that the gravitational force on this entire block is as if it's being applied only at this location, the gravitational torque is going to be trying to twist it in the clockwise direction, and then of course the plane is going to be pushing on it so it can sit in equilibrium, and it will exactly balance it out and give zero torque. So there's nothing that's going to cause it to start rotating around in this direction, because the weight force is trying to get it to rotate clockwise, and the normal force from the plane is just going to keep increasing until it's exactly balanced. Same thing's true here. The weight force is way back here. It's trying to rotate it clockwise around this point, and so the plane can push back and cause it to rotate counterclockwise. Same thing in D. The force down here is trying to get it to rotate clockwise around this point, and the plane can just push back until it's in equilibrium. That is not true in C. Notice that if the center of mass is up here, if the weight force were being applied there, oops, sorry about that, if the weight force is being applied right there, then that means the weight force is trying to get it to rotate counterclockwise about the lower left corner, and the plane has no mechanism by which it can pull back to keep it from rotating in that direction. In other words, if this thing's not glued to the plane can only push on it. It can't pull on it. And in order to keep it in equilibrium, the plane would have to pull in this case. So it can't do that. This thing's going to start rotating about the lower left corner. So it would not be in equilibrium in this case. It would start to tip over and fall down the plane. Maybe you have some intuition about that. All right, that's the end of Chapter 9, short and sweet. You've got some homework problems to practice with this. There's only so many complications. When you first see it, a lot of things look really complicated, and then once you've seen 3 or 4 problem types, it's pretty straightforward. So if you get stuck on some of them, you can always listen to the helpful hints on the Chapter 9 homework.